Okay, so welcome to my CCENT study material. This is Chapter 9, Subnetting with IP Networks. So this goes along with the last several videos dealing with IP addressing and subnetting. So the first thing you have to realize is subnetting is not so much making networks larger, they're about making networks more manageable. For example, I deal with a client that has 3 large locations, maybe 1,000 hosts per network. Well, I could have one giant network that supports all 3,000, or because they're all 3 separate locations, I may have 3 networks that support 1,000. And that's just an example of what we could do with subnetting. It's essentially taking broadcast domains and bringing them in. So in Chapter 9, we're looking at how to subnet. We're going to be talking about address schemes and then some design considerations for IPv6. So upon completion of this, you should be able to at least understand what variable length subnet mask is. I have dedicated videos on VLSM. Given a network, you should be able to calculate the subnet, first usable, last usable, broadcast, network IDing, explain kind of how IPv6 address assignments are implemented in a traditional business network, and basically describe what IP communication protocol is and how to identify a device on a network. Again, all of that's dealing with just our individual IP addressing. So let's start off with subnetting IPv4 networks. Again, the formal definition of subnetting is the process of segmenting a network into multiple smaller networks. These spaces are called subnetworks or subnets. So we're taking a large network and we're carving it up. Large network segments into smaller subnetworks, creating a small group of devices and services too. Normally it serves 2 purposes: control traffic by containing broadcasts, as well as reduce overall network traffic to improve network performance. So again, subnetting larger networks into smaller networks, and those are the 2 primary reasons: controlling broadcasts and to improve or increase performance. So communication between subnets, they are different networks, meaning they must go to a layer 3 device. So how do we make plans for our network? I work at a college. So a college may be 3 separate VLANs, one for the students, one for faculty, one for the administration. So how exactly do we do this? So we can borrow bits to create subnets. So if we're looking at an address space of 192.168.1.0, let me grab my pen. This will be the network portion. You know that because the subnet mask will be 255.255. That means they are locking in the first 3 octets. The last octet is all zeros. That's our host portion. That's what we get to play with. Now, if we want to segment, if we go back to this chart right here, we look at these 8 zeros. If we start from the far right and we just start with 1, and we double it, I don't like drawing with a mouse, but that's the 8th, 7th, 4th. You notice there's 8 spots. Each one of those zeros correspond to a spot. If we move 1 spot to the right, if we change that to a 1, we borrow 1 bit. We now can take that and we can have that as a range. That is a group of 128 because that's in the 8th spot. So this new subnet will be between 0 and 127. That's 128 spots. If we borrow 2 bits, now looking at this guy right here, that's going to be groups of, what position is this? 64. So that'll be between 0 and 63. So forth and so forth. So let's go back to the first example. So that means the first subnet will be this. The second subnet should be, because they're groups of 128. So that's how they get this. How do they get the /25? Well, here's 8 bits. Here's 8 bits. Here's 8 bits. So that's 8, 8, 8, and 1 bit. That means 8, 16, 24. So that's why we get our /25. So hopefully that makes a little bit more sense how we do our subnetting. Again, I have dedicated videos on subnetting. If you have issues, watch them. So how do we get our usable? So if we know we can use between 0 and 127, that's our ID. That's our broadcast. That means the range is anything between those two numbers. So so that's how we get our range. So first usable is 1 greater than the ID. Last usable, 1 less than the broadcast. But again, the address range is anything in between them. So how do we calculate the number of subnets? So to calculate number of subnets, we take 2 to the power of how many bits borrowed. So here we borrowed 1 bit, so 2 to the power of 1, there will be 2 subnets. If we borrowed 2 bits, 2 to the power of 2, there'd be 4 subnets. How many hosts do we have? We look at the remaining zeros. So we borrowed up here 1 bit. There are 8 bits remaining, so 2 to the power of 7 will equal 128. That's how many addresses. We are losing 1 for the ID, 1 for the broadcast. So if we actually take 2 to the power of 7 minus 2, number of usable addresses, 126. That's how we do those calculations. So creating 4 subnets, again, if we borrow 2 bits, we'd be doing groups of 64. So we'll have 4 subnets, 0 to 63, 64 through 127, 128 through 191, 192 through 255. If we're looking at how many hosts per subnet, we already know there are 6 bits. So 2 to the power of 6 minus 2, that will yield us 62 usable per network. How many networks will it yield? 2 to the power of how many bits we're borrowing. We're borrowing 2 bits. So that'll yield us 4 networks. If we want to create 8 subnets, again, we borrow 3 bits. If we look at 2 to the power of 5, that's going to be groups of 32. If we do 2 to the power of 5 and we subtract 2, we're getting 30 addresses per network. And they just take this example over and over and over again. So let's look at if we do an 8th subnet. Where does that apply? So you're going to notice /27. So this is 1 network, 2 network, 3 network, 4 network, 5 networks. And we still have additional space for growth. So, considerations when we're looking at host requirements. The number of subnets required, first of all, and the number of hosts required. If we need 1,000 hosts, but we also need 500 networks, is that going to be realistic? So we have to keep that in mind. Again, the formula to determine number of usable hosts, 2 to the power of n, where n is the remaining zeros after you borrow, subtract 2. That gives you number of usable hosts. Why do we subtract 2? We subtract 2 because we cannot use the ID or the broadcast. Okay, so moving on. Calculating the number of subnets. Again, 2 to the power of n, where n is the number of bits borrowed. So if we're borrowing 2 bits, 2 to the power of 2 will equal 4 subnets. We're borrowing 3 bits, it's 2 to the power of 3, that's 8 subnets. If we're borrowing 4 bits, that's 2 to the power of 4, which is 16 subnets, and so forth and so forth. So subnetting to meet network requirements, you'll notice that sometimes our networks may vary. So sometimes we're going to have different subnets depending on different requirements. Here we have 40 hosts, 20 hosts, 20 hosts, 20 hosts, 15 hosts. Well, the network that will manage the 20, 20, and 20, and probably the 15, is going to be different from the network that manages the 40. So we could end up with maybe, instead of doing all /26s, /26 should yield us all, I believe, 62 hosts per subnet. We may not need them. We may need /27s for the ones that have just 20 hosts. But if we want to be uniform, we'll use /26. This is wasteful. So traditionally, we would all do equal sizes. But with variable length subnet masks, we create the subnet depending on the networks. For example, we may end up with 1/24. Sorry, I take that back. We may end up with 1/26, and we may end up with several /27s. But if we're talking about interconnection networks, they may only need 2 usable. So we may only use a certain amount of them. That's what these /30s are for. These will be used for our networks that are going to be probably around 20, anything less than 30 usable. So let's see this in an example. Here's one network with one subnet mask. All of these can change depending on requirements. But you'll notice here, it's not a /27, it's /30. That's it. That way, we can use this more efficiently. So with our /27s, we could have our 4 buildings with the appropriate networks, with the appropriate subnet masks. And then we could have our WAN connections, the connections between routers, using our /30s. So let's go ahead and get into address schemes. So the next fun topic is always one of my favorite, which is address schemes. And that's because, well, when you design a network, you have to understand how they flow and kind of stay with the same flow. For example, maybe we set it up so that the host devices may use 1 through 229. As long as you're consistent with your network planning, that's okay. It's just you have to document and you have to be consistent. For example, in our environment, I like to use between 240 and 250 for all of our printers. I like to use 253 as our gateway. I like to use a specific range of addresses, but it doesn't really matter how you do it as long as you stay consistent. So let's move on to design considerations for IPv6. And again, very similar to IPv4, except we're in hexadecimal. And so we're dealing with, again, hextets instead of octets. It's the same design principles. It's hierarchy. Here, range of addresses, so forth. Here you're going to notice this is the different networks. Even though the first hextets are staying the same, the fourth hextet is changing. That's how we're separating our network ranges. And here we're changing this one all the way to F. So we're incrementing by 1 bit or 1 hexadecimal bit, which is actually 4 real bits. And actually, that's it for this chapter. We went over basic VLSM, we went over basic subnet calculations, basic subnet host calculations, sizing requirements, things of that nature.